Lesson 37 demo. In this class, we do the activity before the demo. So if you haven't done the activity yet, go ahead and do that and possibly watch the video for the activity before watching this demo video. Here's the notation for finding the left and right sums as we did in the activity. Warning, lots of notation ahead. Let v equal f of t be a non-negative velocity function on the interval a less than or equal to t less than or equal to b. So here's the idea. This is our zombies velocity function, and the given starting times are a and b, just like in the activity where we went from 0 hours to 5 hours. We will cut this interval into n equal pieces, which will give us a set of equally spaced t values called t0, t1, t2, all the way up to tn. We're just trying to generalize what we did with the zombies. So going back to the zombies, we had 0 to 5 hours. And in one part of this problem, we cut this into 1 hour increments, not equally spaced here. But then for another part of this problem, we actually cut it into not 5 1-hour increments, but 10 half-hour increments, right? So 0.5 there and 1.5 there. The important thing is that we just cut this into a bunch of different pieces. We'll assume that they're equally spaced pieces, although at the end of the day, they don't have to be. But we're trying to generalize. So instead of saying 5 equal 1-hour pieces or 10 equal half-hour pieces, let's just call it more generally n pieces. And the names of those pieces, instead of being 0 and a half and 1 and 1 and a half, are going to be generally called t sub 0 for the first time, and t sub 1 for the second time, and t sub 2 for the third time, and t sub n for the last time. Then the width of each interval is given by delta t equals. All right, so if I tell you that we're going from 0 hours to 5 hours, and we're cutting this into 10 equal pieces, how would we know how long each piece is? Well, we know that they're all half an hour, right? And the reason they're half an hour is because we're taking the total distance of 5, which is really 5 minus nothing, and we're cutting it into 10 equal pieces. And so that reduces to a half. And so in general, the delta t, the width of each of those little spaces, is b minus a, that's like 5 minus 0, divided by the number of pieces. It's called n in this setup. Okay, remember our big conclusion from the zombie race: if we have a graph of velocity, then the total distance traveled is the area under the graph. So in this particular case, the actual distance traveled will be the area between these vertical lines here and the x-axis and the curve. And so I'll shade that in here. But the actual distance traveled would be exactly equal to this area here. Now, finding the areas of curvy shapes is really, really hard, which is why we drew rectangles instead. But anyway, the exact distance traveled is equal to the exact area under that curvy shape. We can approximate the total distance traveled by the left-hand or right-hand sums. Formulas are given there. Looks like a lot of notation. I want you to understand it. It's really not complicated once you think about the pieces. So let's take a look at this very first rectangle. Okay, so in this first interval, we are going to draw a left-hand rectangle, which means of the 2 points that determine this first interval, we're just going to pick the left-hand one to dictate the height of the rectangle that we're going to draw. So we pick the left-hand point, and we complete this thing to make a rectangle. And let's do one more. Let's do this interval here. And again, we're going to consistently always pick the left-hand point to dictate the height. So the left-hand point has a height on the curve way up here, and we're going to use that point to complete the rectangle. I'm not saying that that particular rectangle is like is always above the curve or it's always below. In this case, I actually think it's partially above and partially below, and that's okay. So all we're going to do is every single interval pick the left-hand point, find the height at that point, and complete to a rectangle. And so let's look at the area of the red rectangle. We know that the area of a rectangle is base times height, and the base is given by the horizontal length right there, and the horizontal length is symbolized by delta t. That's what we called horizontal length. And the height is really the function value. The function value where? The function value at the left-hand point in that red first interval. And the left-hand point is called, it's called a, but let's call it t sub 0. So that's the area of that first rectangle. Just know, like this height right here, maybe better. This number right over here is simply the function value at t0. Okay, let's do one more. The area of the blue rectangle is equal to the base times the height. The base is the length of the horizontal blue line, which is also delta t. We're assuming equally spaced points here. And then the height is given by whatever this y value is up here, but that y value is simply f of this particular point, the left-hand point in this case, which is t1. And so it's delta t times f of t1. And so that's it. If we want the total area of all of these rectangles, including all the ones I didn't draw, we would just add these things up. Delta t times f of t0 plus delta t times f of t1, there and there, plus delta t times f of t2. Just have to be careful at the end. What's the last one that we pick? So in this last interval, again, we're always picking the left-hand endpoint. So we'll use a left-hand endpoint and complete to a rectangle. So the last point that gets picked is this t sub n minus 1. And so that's why this one ends at t sub n minus 1. And the last rectangle never actually sees t sub n. So there's no t sub n in this calculation. Okay, so we can do the same thing with right-hand sums. The picture is already kind of cluttered. I guess I'll just erase everything. And we'll just do 2 rectangles for right-hand sums. So in the first interval, right here, in every interval now, we're going to pick the right-hand point to complete the rectangle with. So we go to the right-hand point, we go up to the curve, we complete a rectangle, which means in this case drawing left and then down. And in the next interval, we pick the right-hand point, we go up to the curve, complete to a rectangle. There's no space between those rectangles, but I just want us to see the red and the blue. And so in this case, the area of the red, base times height. Base is always delta t. Height is now given by the height at t sub 1. So it's f of t sub 1, which means f of t sub 0 is never calculated for the right-hand rule. Area of blue, base of the blue one is still delta t. And now which point gave us the height of the blue rectangle? It was the one at t2, so f of t2. And if we look at the very last rectangle, picking the right-hand point, it's off the screen, but that's okay. Imagine completing it. So that means that the very last one is going to be f of t sub n. So this last one does get to t sub n. That one didn't. But this one does not have a t sub 0, and this one does. So you can see the f of t1, f of t2, there, and then ending at f of tn. Okay, so I think that is good there. All right, number 3, also notice that the area of a single rectangle is our approximation for the distance traveled in a given time period. I wrote it here as base times height, but we wrote it in the activity as velocity times time. Okay, number 4, what happens if the velocity is negative? Let's find the distance traveled between t equals 1 and t equals 4 using the velocity curve that's pictured, and then we'll answer something else. So we're going to do this one exactly, not using left or right-hand sums. Okay, so we're looking between t equals 1 and t equals 4. Let's find those points. T equals 1, t equals 4. And I'm going to go ahead and draw the area under the curve. So bounded by those two things there, x-axis and then a vertical line, and the curve. So it's the area, it's always trapped. It's not, you can't say it's the area below. You got to say it's the area between the function and the x-axis or t-axis. So it's this area here, and then between the function and the x-axis is actually above the function here. So the reason we don't need to approximate that area with rectangles is that those are triangles, and areas of triangles are easy to find. So distance traveled is equal to the area of those triangles, area of triangle 1 plus area of triangle 2, we'll say, equals, okay, let's do the area of triangle 1. We know that it's half of the base times the height. So the base of the left-hand triangle is 3 minus 1, that's a 2, times the height, that looks like it gets up to 4. Great, plus. And now for the lower triangle, half base times height. Base in this case goes from 3 to 4, that's just a 1. And the height in this case goes down to -2, so that height is 2. And so we just crunch the numbers together. Let's actually do them separately first. So the first one is a 4, and the second one is a 1. So altogether, the total distance traveled here is 5. But then there's a follow-up question. It says, for that same interval from 1 to 4, find the value of the other D word that's related to distance traveled. Okay, so the other D word that I'm talking about, maybe I should write the word distance here. So the D word that I'm talking about is displacement. So distance just means how far you traveled, regardless of direction. We didn't pay any attention to direction, but this particular person, if we imagine this person was moving along the x-axis, let's go ahead and put the person right here at t equals 1, and let's assume that when the person's velocity is positive, they went to the right on this horizontal line, and when the velocity is negative, they went left. And I'm not actually going to put, I guess we can put some numbers here, but let's suppose that that we call this thing here position 0. It's at time 1, but I'm just going to call that the x-axis at position 0 right there. And so what we saw here was that in the beginning, between t equals 1 and t equals 3, this person's velocity, well, it was decreasing, but it was positive the whole time. And so that means during this entire period, the person is moving to the right in the positive direction. And at the end of the day, this person moved a total of 4 units to the right. So that means that we can put another dot over here and say that when we got to t equals 3, we have moved 4 units to the right. But then between time 3 and time 4, this person's velocity was negative. And altogether, this person moved a total of 1, but in the negative direction. And so our last point is actually right here. T equals 4. I know it looks weird that t equals 3 is to the right of t equals 4, but time isn't really something we can see here. I'm looking at the x-axis. And this person went 1 unit to the left. And I know that it was 1 unit to the left because that was the area of the triangle below the t-axis. And so I know that going from 4, 1 unit to the left will land them on 3 on the x-axis here. And so if I ask the distance this person traveled, well, the person traveled 4 and then 1, and the total distance traveled is 5. We got that right. But the displacement is a measure of how far you have moved from your starting position. Doesn't matter how inefficient you were getting there. It's just how far are you from where you started. And so the displacement in this case is just 3. This person ends up 3 units away from where they started. How could we do that using the calculations without trying to draw this x-axis every time? Well, it was a positive 4 for the top triangle and then a negative 1 because the other triangle was below the x-axis. So that gives us our 3. So distance is just a measure of how far you've traveled altogether, but displacement is just how far are you from home at the end of the trip.